Classification of AGN. AGNs are classified into many types depending on the viewing angle from the viewer. Although there are many types of classification, basically AGNs are classified in two categories: radio loud AGN and radio quiet AGN. If the ratio of the flux at radio frequency to the flux at visible frequency is greater than 10, it is called radio loud active galaxy, otherwise radio quiet active galaxies. The observational classification of AGNs has following types with their detailed description. Low ionization nuclear emission line regions, liners. Liners are the least luminous active galaxies in the AGN phenomenon. These galaxies are very common and are easily detected in nearly 50% of all spiral galaxies, Ho et al., 1994. As the name suggests, these systems show only weak nuclear emission line regions, and no other signatures of AGN emission. The non-stellar luminosity of most liners is small compared with the stellar continuum, Netzer, et al., 1990. The strongest emission lines are of low ionization species and are narrower, with 200 to 400 km per second, than the narrow lines of Seyfert galaxies. Spectroscopically, liners resemble Seyfert 2 galaxies, except that the low ionization lines like oxygen 1, 3600 A, and nitrogen 2, 6548, 6583 A, are relatively strong. It is debatable whether all such systems are true AGN, powered by accretion onto a supermassive black hole. If they are, they constitute the lowest luminosity class of radio quiet AGN. Seyfert galaxies. Seyfert were the earliest distinct class of AGN to be identified. A Seyfert galaxy has a quasar-like nucleus, but with a clearly detectable host galaxy. They are active spiral galaxy with nuclei which have bright emission line including visible wavelength and show optical range. Nuclear continuum emission, narrow and broad emission lines, i.e., Lyman alpha, nitrogen 5, silicon 4, helium 2, oxygen 3 forbidden, carbon 3 forbidden, magnesium 2, occasionally strong nuclear X-ray emission and sometimes a weak small-scale radio jet. The emission lines had Doppler widths corresponding to velocities of several thousand km/section. The Seyfert galaxies constitute the low luminosity end of the AGN phenomenon and have usually low redshifts. Based on width of emission line caused by the effect orientation of the galaxy with respect to the observer from Earth, Seyfert galaxies are divided into two as follows: Seyfert 1, Type 1. Seyfert galaxies have very broad emission lines that include both allowed lines, hydrogen 1, helium 1, helium 2, and narrower forbidden lines, such as oxygen 3 forbidden. The width of the lines is attributed to Doppler broadening, indicating that the allowed lines originate from sources with speeds typically between 1000 km per second and 5000 km per second, while the forbidden lines correspond to speeds of around 500 km per second. Seyfert 2, Type 2. Seyfert galaxies have only narrow lines in both permitted and forbidden type, but still wider than emission lines in normal galaxies, with characteristic speeds of about 500 to 1000 km per second. The basic idea is that the differences between Seyfert 1s and Seyfert 2s are caused by an orientation effect. The broadline region, BLR, and continuum source are blocked from our view in Seyfert 2s by thick obscuring material, presumably a dusty torus, Antonucci and Miller 1985, at large inclination angles, while they are observed directly in Seyfert 1s. Quasars. Quasar stands for quasi-stellar radio source. They are believed to the most luminous and energetic object in the universe, powered by the accretion of matter onto supermassive black hole. Such objects are also called as quasi-stellar objects or QSOs. Their luminosity is about 10 to 100,000 times luminosity of our galaxy and about trillions time luminosity of our Sun. Quasars were discovered in 1963 as radio telescopes began to be able to pinpoint sources of radio waves more precisely, and 3C273 was the first quasar to be studied by Martin Schmidt. The quasars are characterized by their unresolved nuclei, time-variable non-thermal continuum, broad and strong emission line with large redshifts. They have approximately similar broad spectral energy distribution, said, spread across 7 orders of magnitude in frequency. Based on the radioluminosity, the quasars are subdivided into radioloud, RL, and radioquiet, RQ, quasars. Some quasars show an excess continuum emission in the blue to UV part of the spectrum and is called as Big Blue Bump, BBB. The BBB component is attributed to the thermal emission from a hot accretion disk of temperatures around 30,000 K surrounding a supermassive black hole. Some astronomers argue that it might be due to free emission. Blazars. The word blazar was coined by Spiegel in a banquet speech at the Pittsburgh meeting on BL-Lacerdae, BL-Lac, objects, Wolf, 1978. They are a subclass of AGNs more like quasars but characterized by the presence of relativistic jets that point directly at Earth. The characteristic properties of blazars are, strong optical polarization, violent variability, a compact flat spectrum radio source and a very smooth featureless continuum spectrum. The most well-known object in this class is BL-Lacerdae, found in the northern constellation of Lacerda, the lizard. BL-Lacs are distinguished by the absence of strong emission or absorption lines in their spectra. BL-Lac objects, high polarization quasars, up to 30%, and OVVs are combinedly called as blazars. Blazars are highly variable sources and often undergo rapid and dynamic fluctuation in the brightness in the timescale of few hours to days. Radio galaxies are a class of extragalactic objects characterized by their strong emission of radio waves. They are usually associated with massive elliptical galaxies and their nuclei emit jets of high-velocity gas above and below the galaxies. This radio emission is typically observed at various radio frequencies, often spanning from megahertz to gigahertz. The intensity of radio emission can be millions to billions of times greater than what we observe from our Milky Way galaxy. As the jets travel away from the black hole, they can extend for vast distances into intergalactic space. The radio waves are produced as these high-energy particles interact with the surrounding magnetic fields, emitting synchrotron radiation. Like Seyfert galaxies, radio galaxies may also be divided into 2 classes: broadline radio galaxies, BLRGs, corresponding to Seyfert ones, and narrowline radio galaxies, NLRGs, corresponding to Seyfert 2s. Radio-loud galaxies have extremely powerful radio emissions, often associated with very strong and extended radio jets, while radio-quiet galaxies have relatively weaker or no significant radio emissions. BLRGs have bright, star-like nuclei surrounded by very faint, hazy envelopes. NLRGs, on the other hand, are giant or supergiant elliptical galaxies, type CD, D, and E. Ultraluminous far-infrared galaxies. Ultraluminous far-infrared galaxies, ULIRGs, are a class of galaxies known for their extraordinarily high levels of far-infrared, FIR, emission, indicating intense star formation and, often obscured active galactic nuclei. Far-infrared radiation refers to the electromagnetic waves with longer wavelengths than those in the visible and near-infrared parts of the spectrum. The Infrared Astronomical Satellite, IRAS, has discovered a highly luminous class of infrared galaxies, which emit over 90% of their total energy in the far-infrared, FIR, region, Soifer et al., 1987. These galaxies have their FIR luminosities more than 1 trillion LSUN and exceed optical luminosity by a factor of 10 or more.